Right, today we have to finish up lesson 2.3, so let's warm up with number 4 on 5A. And they want us to perform synthetic division on these polynomials. So remember, synthetic division is the one where you have this weird little half box, and then you're going to write some coefficients, leave a little space for your work. What goes in the half box, though? That would be the solution to your divisor. So think about solving that divisor, and you'd put a 1 in the box. Be careful when you tell me your coefficients. Remember, your coefficients are in your dividends polynomial in standard form order, all the way from lead term all the way down to the constant. So your lead coefficient here would be a 1. Then what? Careful, there's a missing cubic term, so 0. And then -3 is the quadratic term. Then what? 0 again. The linear term is missing, see it? And then all the way down to the constant of 12. So to get your synthetic division started, you need to bring down your first term, and that's the beginning of your multiplying step. So 2 steps here, you're going to multiply, and then you're going to add them up. And then you repeat. Multiply, add them up, and multiply, add them up, and one last time multiply. And then when you add up these last 2 terms, you have a 10. This last number is something special to the problem, though. What is this last number? That's the remainder. So if they want me to write the quotient out, the downside to synthetic division is you don't actually get an answer once you perform it. You get the coefficients to your answer. So your lead term is x to the 4th, and you were dividing it by the lead term of x to the 1st. So your first term of your quotient is going to be 1x to the 3rd. And then from there you move down standard form. So 1x to the 3rd plus 1x squared minus 2x, and then this must be the constant. And then how do I write this remainder? He's remaining in the division problem, so he's still being divided by the x minus 1. So that's the drawback to synthetic division. The math is really easy, but then the interpretation of the answer is a little odd. Okay, on the back. So we're still in lesson 2.3. We're looking at worksheet 5B next, and we're going to discuss what's called the remainder theorem first. So the remainder theorem says that if you have a factor that you divide into your polynomial and you get a remainder of 0, that means it divided in evenly. Thank you. That means a couple things for us. So that factor that you try to divide, if it divides in evenly, then it is a factor, meaning I can use that technique for factoring in our upcoming lesson. This is one of those moments in math where like all the days blend together into one gigantic lesson. Remember, we're shooting for a fundamental theorem of algebra here. This is like the whole weeks of our work is one gigantic theorem. So you're going to feel like, isn't this the lesson we already did? Like when we learn the next lesson, and that's the right answer. They're all kind of blending together. So we're going to decide to probably do synthetic division most of the time, unless you really have a passion for long division. Anyone have a deep-rooted passion for, no? Okay. Just me? All right. Synthetic division's easier, let's be honest. So if given a choice, synthetic division's probably the way to go. Now, there's also a fun little theorem out there that they stumbled upon, that if you're trying to substitute in a value, instead of plugging in the value, like 4, -7 to the 4th power minus 7 times -7 to the 2nd power, like that's kind of hard to do in your brain, right? You'd probably want to hope for a calculator if you're doing that question. Well, you can actually use synthetic division setup to do what's called synthetic substitution. That's kind of cool. So we'll hit both of those topics in a moment. This is not on your paper, but it is from your book. It says, it's discussing the synthetic substitution component of this theorem, that if you had a polynomial like this, and they wanted you to plug in x equals 12, is there any chance that you'd want to do that by hand, like the old-fashioned way of like plugging in a 12 for all of your x's? Me neither, because like right away, 12 to the 3rd power. Anyone have a thought about what 12 to the 3rd power is? No, I mean, I could figure it out. It's like whatever 144 times 12 is, but that feels like 4th grade math. No, thank you. Without a calculator, cheater. So the point is, no, we don't want to do that by hand, but turns out that if you were to set up synthetic, it looks like synthetic division, right? Except this time you just put the 12 in the box. You don't do anything with like solving because there's nothing to solve. If you perform synthetic substitution, your remainder is actually the answer. So apparently, if you were to plug in 12 into this polynomial, it comes out to 650. Now if you look at the nature of the problem there, like the biggest thing you had to do was 48 times 12. So like if you were really in a jam without a calculator, you guys could figure out 48 times 12. I know you could. So that's the benefit of synthetic substitution. So little offshoot of the remainder theorem that we'll discuss. All right, here we go. First, they want me to use synthetic substitution to find f of 2, meaning they want me to plug in 2 to the function. So instead of directly substituting in the 2, let's try this neat little synthetic substitution thing. So in the box, you'll put a 2. And then you need to show me the coefficients of what the polynomial that you're trying to plug into. So what do we have here? 2, 5, negative 14, and negative 8. And according to the remainder theorem, that after I perform this, whatever I get down here, that's my answer. So, same steps, guys. Multiply, add. Multiply, add. Multiply, add. And multiply, and add. So apparently, if you were to plug in 2 to this polynomial, it comes out to an answer of 0. That's good to know. Now they have a follow-up question. It says, so think backwards to the factor theorem. When you do synthetic substitution with a 2, and you think back and think of that as a factor of x minus 2, since the remainder came out to 0, and they ask me, is it a factor or not, the answer to this question is yes. X minus 2 divides evenly into the polynomial, so he must be a factor component of that polynomial. So you're probably wondering, why do I care about that? You'll see. Like, next. All right, skip to number 7. I want to know this polynomial. I want you to write it in factored form. So for most kids, they look at that and they go, all right, it's 4 terms, so I'll try factor by grouping. Yeah, go ahead. Try grouping that. Remember the whole thing about factor by grouping is the parentheses have to match? This is not going to work out with factor by grouping. Factor by grouping only works when you have real coefficients and rational coefficients. And if it's set up in a certain way. Now, what do we do then? Here's what's going to happen. For today, I'm going to give you a little hint. I'm going to say, one of the factors is x plus 5. So what we're going to do then is we're going to set up synthetic division with this polynomial and that divisor. So in the box goes the solution to the factor. So the solution to that factor would be negative 5. And you set up your coefficients like before. Now I told you that this is a factor, so what should be your remainder down here, guys? We should get 0 for a remainder. So if I don't get 0, either my teacher lied to me or I screwed up my math. It's always possible that I lie to you. All right, here we go. 1 times negative 5 is negative 5. Negative 2 plus negative 5 is negative 7. Negative 7 times negative 5 is positive 35. Negative 29 plus 35 is 6. 6 times negative 5 is negative 30. And turns out, teacher didn't lie today and we didn't mess up. The remainder is 0. So that tells me that yes, x plus 5 was a factor. So what do we have left? Think about what you started with, guys. An x to the third divided by an x to the first. So this term is going to be 1x to the second minus 7x plus 6. And my job is to factor this polynomial. Well, guys, this is an Algebra 2. Actually, that's an Algebra 1 question. You can factor this. This factors into x minus 6 times x minus 1. So it says, what is f of x in factored form? So then this is the problem I get from kids. They go, oh, well, it's x minus 6 times x minus 1. Is that equivalent to the original problem? No, there's a whole other factor that we used early on that you were totally forgetting. What is it? The x plus 5 is also a factor. Does it matter what order I write these factors in? No. Commutative property says no. All right. So we're going to use synthetic division to kind of help us out to break down really large polynomials all the way down to something that I can manage factoring, like a quadratic. All right, here we go. This time, what I'm going to do is I'm going to be extra nice on this problem. I'm going to give you two factors. So we're going to do synthetic division once, and then we're going to come back and do what's called a successive synthetic division, so twice. And then we're going to end up with the last factor. By the way, if this is a cubic, how many factors should I be getting in theory if it's a cubic? I should be getting 3 factors at the end of this problem. All right, let's find out what we have. First clue, it says x plus 4 is totally going to be a factor. So let's set up synthetic division. We're not missing any terms this time. So 2, -1, -41, and -20. Is this one on your notes? Oh man, all right, we'll do it anyways. The solution to that factor though would be a -4. So just watch. Okay, bring down your first term, and let's multiply and add. So this is -8. -1 plus -8 is -9. That's 36. -41 plus 36 is -5. That was really difficult for a minute. -5 times -4 is 20. -20 plus 20 is indeed 0. So teacher didn't lie to me. That is a factor. Now what we're going to do is called a successive synthetic division. Keep your new polynomial, which is this dude. Don't bother writing it back in polynomial form because I'm going to have you do synthetic division again. So here's your new start. Forget this. That's gone. Got another synthetic division coming up. But this time, the factor that I want you to consider is the factor x minus 5. So what should go in the little box here? +5. Good. So 2 times 5 is 10. -9 plus 10 is 1. 1 times 5 is 5. And then -5 plus 5 is 0. As my teacher promised, that was a factor, which means the remainder should have come out to 0, which it did. So what do you have left? This is kind of strange. Think about what happened here, guys. You took 2x to the third, and you divided it by an x term, but then you divided it by another x term. So you divided it by x squared. So you should have left 2x as your first term, which makes sense, because look what we have here, guys. 2x plus 1, no remainder. So one of my factors is that 2x plus 1 you just stumbled upon. What's another factor? The ones they gave you, yeah, x minus 5 and x plus 4. So that's kind of a cool technique. If you happen to know more than one factor, you can do successive divisions and whittle yourself all the way down to the smallest possible polynomial. So for us, that would be a linear. All right, this one is on your notes, I believe. Number 8. Okay. They want us to graph first. This is kind of a lead into tomorrow's lesson. Can you guys go and type this in Y1? All right, so once your polynomials graphed in Y1, I mean, the window's not great. All I'm really interested in is whether those factors were going to be zeros of the polynomial, and it does say to graph. So what they want me to look at are all the x-intercepts. Oops, my bad. So the first one says x minus 1. Is x minus 1 a factor? Well, if x minus 1 is a factor, that means you should see an x-intercept at x equals 1. Is that happening? No, so put a no on that one. And then it says, how about x plus 2? Well, if x plus 2 is a factor, that means you should see an x-intercept at x equals -2. Is that going on? Sure is, so put a yes next to that one. And then, let me erase some of this. And the last one is x minus 2. Well, if x minus 2 is a factor, then that means x equals 2 would be an x-intercept. Is that happening? Yes, it is. So what we're going to learn in our upcoming lesson is there's before the days of the graphing calculator, this was a really terrible question, because there's a theorem coming up where you could make some educated guesses as to who the factors were, but you still had to check all of them, and you'll see what I mean in the next lesson. It's not great. But being 2018, we have a graphing calculator that's going to kind of guide us in the right direction. So I can see that x equals -2 and x equals +2 are good places to start, because I can see that their x-intercepts and their zeros of the polynomial. The reason I needed two things to kind of help me out, guys, is right now you are looking at a quartic, and it's not the kind of quartic that I can factor. So in order to whittle it down to something manageable, aka a quadratic, I'm going to need to do 2 synthetic divisions. I need to knock it down 2 levels. So, what'd you guys tell me this was? No, that was a no, wasn't it? Oop. This one was a no, this one was a yes, and this one was a yes. So those are the 2 we're going to use in synthetic division. It does not matter which one you use first versus second, so I'll let you guys decide. Do you want to use -2 or +2 first in the first division? +2. You're a positive kid, right? Here you go. +2 in the box. And coefficients. Watch out for missing terms. This time we don't have any. Okay, here we go. Now, according to our calculations, this should come out to a remainder of 0. Otherwise, we have either made a misguided judgment or we just screwed up. Let's see. 3 times 2 is 6. 8 plus 6 is 14. 14 times 2 is 28. -15 plus 28 is 13. Yeah? Okay. You know I like confirmation, guys. All right. 13 times 2 is 26. And that would be a -6. And then -6 times 2 is a -12. All right, I'm feeling good now because the remainder came out to 0 as it should. But right now you have a cubic. That is too out of control for us. We need to break it down to a quadratic. So let's do these steps one more time. But this time with the other factor that we found on the calculator, which was the factor of x plus 2, which is a 0 of -2. All right. So your goal is to get this down to a quadratic. Then I can handle a quadratic. So let's see. -6. 14 minus 6 is 8. Let's see. That's a -16. 13 plus -16 is -3. And then -3 times -2 is +6. Add those up and we do indeed get a 0 there. So good. Feeling good. Feeling even better because now I have something I can handle. This is a quadratic. I took a quartic and I knocked it down 2 times, so now it's a quadratic. This is 3x squared plus 8x minus 3. And now what do they want? They want me to write this in factored form. Well, guys, you can factor quadratics. Come on. You got this. What times what will give you 3x squared? That's right, class. 3x and x. You're whispering it. And then 3 times 1 is going to be the 3 on the back end. Just be careful where you're placing the 3. Let's put a +3 right here and a -1 right here, because that'll be a 9 minus 1. So somewhere on my paper it said f of x in factored form. I think it's on the next... Oh, no, it's nowhere. Do you have a line for that? Okay, I don't. So factored form would be, all right, the ones I just found, huh? 3x minus 1. And the other one I found was x plus 3 through factoring. So is that it? Is that the whole polynomial? No, why not? There's 2 more that we used. I just can't forget about them. So there was x plus 2 and there was x minus 2. So this is your polynomial f of x in factored form. And I bet there's a follow-up question after it. Does it say, so the zeros are? So the zeros are... Go ahead and solve each of those for me, guys. The first 0 here would be a 1/3. The next 0 would be a -3. And then we already knew there was one at -2 and +2. So that was fun. That's a little dive into the history of math. Can you imagine doing that without a graphing calculator? No? Oh, you're gonna. All right, so that completes lesson for 2.3. We're going to switch over to lesson 2.4 and get through as much of it as we can. It blends with 2.3 very nicely. So find worksheet 6. So for lesson 2.4, worksheet 6, we're going to run right into what's called the rational root theorem. So this one is like back in the day, like old people say, back in my day, we didn't have graphing calculators. Now, that I can't really get away with that because we totally had graphing calculators back in my day, but I still had teachers who made me do this by hand. And it is still important for you guys to know how to find these if ever in a moment where you don't have a graphing calculator. So the rational root theorem states that if you can identify P and Q, okay, that's awfully confusing. P and Q are the first and last coefficient of the polynomial. So, this general form doesn't really help you any. What they're referring to, look, write down this formula if it's not anywhere on your paper. This is the best formula for you. It's plus or minus in front of this, but then it's the factors of the constant divided by the factors of the lead coefficient. So just write down that formula. The general formula from your book is awfully confusing. Like everything in math, the minute they stop calling them what they are and they call them variables, it gets super weird. And then let's see an example of what this looks like. So the rational root theorem is a way for you to come up with all the possible places to look for rational roots. Now notice I said rational roots. It has nothing to do with imaginary or irrational roots in general. So, remember that question before where we looked at our graphing calculator and we saw like it crossed at x equals 2 and x equals negative 2? Well, if you don't have a graphing calculator, you won't be able to do that step. So you have to use what's called the rational root theorem. Here we go. This question is, yes, it is on your paper. So what you do is you look at the constant and you look at the lead coefficient. By the way, what is the lead coefficient here? It's a 1. So what you would do is you'd talk to me first about the number 6. What are all the factors of 6? Well, they wrote this out for you already. And they put a plus or minus in front of all the numbers. I don't like that. What I just do is put a plus or minus in front of my list. It's a little lazy of me, but sorry, that's what I do. So do you guys agree that 1, 2, 3, and 6 are all the factors of 6? Yeah. And then 1's a pretty easy question. The only factor of 1 is 1. So then what they do is they set up fractions where all the factors of the constant are up in the numerator as a possibility, and all the factors of the coefficient are in the denominator. So the way I would read this, I would write plus or minus, and then I go through my list. So like 1 over 1 is 1, 2 over 1 is 2, 3 over 3 is 3, 3 over 1 is 3, 6 over 1 is 6. Then, we lucked out here, guys. There's nothing else in the denominator, but we're going to see a problem coming up where like it's something other than 1. Like for instance, if it was 5. The factors of 5 are 1 and 5. So then you'd have to come through and divide all of them by 5. So this list can get pretty intensive. Now what is this list, you might ask yourself? Well, there's a list of 8 numbers that we could, in theory, try. And what does it mean to try? It means to do synthetic division until you get one that has a remainder of 0. Now, literally back in my day, I know I hate saying that, but back in my day, I had to do this, and then they taught us other techniques for making better guesses. So like, for instance, there's a technique out there where if you were to add all the coefficients together of your polynomial, if they cancel out to a 0, that means 1 is a 0 of your polynomial. That's just one of the weird tricks. Okay, I had to learn all these weird tricks because my teachers made me do them by hand. It was horrible and I hated it. So in the spirit of that, I'm not going to make you do these by hand. But here's what I do need, because there is a question on your post-test. You have to be able to come up with the possible rational roots. And then after that, I'm not going to make you guess and check for your whole life. After that point, you're going to go look at your calculator and you're going to kind of visually see, okay, is it 1? Is it negative 1? Is it 2? Is it negative 2? Where does it cross the x-axis? So we're going to do a hybrid of old school and technology because it's 2018. So here's what's happening, guys. On this question, someone already took the liberty of graphing it, and they determined that there was totally an x-intercept at negative 2. So you don't have to do that step, someone already did it for you. So they went through and they did synthetic division, and they whittled it down to a quadratic. So there's your current quadratic, x squared minus 7x minus 3. Now, If I tried to factor that, I'd run out of options real fast. You're not going to get numbers that multiply to -3 and then the arches add up to -7. So if I'm supposed to find all the zeros of my polynomial, what is another way that we could solve x squared minus 7x minus 3 equals 0? Quadratic formula. You could try completing the square. I wouldn't suggest it though. So using quadratic formula, the solutions to this would be opposite of b, so positive 7, plus or minus square root of b squared, so 49, minus 4 times 1 times -3. All of that over 2 times a. Now I already know this is going to come out gross. So I'm going to need you to calculate just the discriminant, and then we'll decide how we're going to reduce this in a minute. Remember all that hard work we did with quadratic formula back in, like a month ago? This is our moment, guys, right here. 49 minus 4 times 1 times -3. Is it 61? Okay. So 7 plus and minus square root of 61 over 2. Oh man, this is great news, guys. 61 does not break down. The square root of 61 is just square root of 61. So we're going to leave it in this form. The zeros are, well, you just found 2 of them. And I don't mind if you guys keep it in the short notation of 7 plus and minus square root of 61 over 2. But that's only 2 solutions, guys. You started with a cubic. So where's the other solution? -2. Very good. The one we stole from the calculator. So that was fun. All right. Next question. I want you to practice just listing out all the possible zeros first, and then we're going to go to the calculator and see if we can easily see all the rational zeros. I think on one of them at least we will. All right, so practice 1. What you're going to do, oh, you know what, before we get to that one, let's do one that's more exciting. This is not on your paper anywhere, guys. Just watch on the board. So on your homework, the first couple questions say find all the possible rational roots. So what you're going to do is you're going to take the constant and you're going to take the lead coefficient. And what I do is I set up plus or minus, and then I write all of my constants factors up top first. So, oh boy, factors of 36. Start listing. 1 and 36. 2 and 18. 3 and 12. 4 and 9. And 6 and 6. Oh boy. Okay. Over. Give me all the factors of 2. 2 and 1, yeah. That's not too bad. But here's the thing, you're not done. Because now what you have to do is go through and list out. I'm not going to make you list every positive and negative one at least, so that's half of the battle. So just put a big plus or minus sign in front of this list, but here we go. All of these divided by 1 would just be all of these. So here we go. 1, 2, 3, 4, 6. Pen, stop doing that. 9, 12, 18, 36. Okay, we done? No, because now you got to take all these and divide it by 2. Okay? So 1/2. Now 2 over 2 is really a 1, but we already listed that, didn't we? So don't write that one again. 3 over 2. Am I going to write down 4 over 2? No, because it's already listed. 5 over 2. No, not 5. Jeez. All right, 6 over 2. No, it's already listed. 9 over 2. Yeah, I got to write that down. 12 over 2. Already listed. 18 over 2. Already listed. 16 over 2. 36 over 2. Jeez. No, it's already listed. So, see, that list didn't get as intensive as you were thinking originally, right? A lot of the things were already listed. That was super fun. Let's not do that anymore. All right, this question is on your notes. So first, list all the possible rational roots. So just like in your homework, you're going to write possible roots. You're going to put down a gigantic plus or minus sign. And you're going to look at the factors of the constant first. And then you're going to divide it by, oh, this is like your birthday, guys. What's the lead coefficient there? Just a 1. So you're not going to have to divide all these by anything extra other than just a 1. Here we go. So factors of 20. 1 and 20. 2 and 10. 4 and 5. divided by 1 will just give you all those. Okay, so now what they would want you to do is go to your calculator, which if you have your calculator handy, please go ahead and type in that function. But it looks like this is the picture. Now guys, originally this question was a cubic. And I'm looking at my picture on the slide here, and I'm visually seeing 1, 2, 3 places where it crosses the x-axis. So it turns out that all 3 of your roots are they're visible on the calculator. Now, without actually finding them and thinking about your possible list here, guys, what do you think this one is right here? You think it's -2? Yeah, me too. And that's one of the numbers in my list. Okay, this next one here, what do you think that 0 is? +2, very good. And then this last one here, what do you think that 0 is? It's a +5, very good. So the actual zeros are these guys. So I don't know if I sold you on the need for the rational root theorem yet, but it is necessary on your calculator, because I think we've all seen a moment where our calculator gives us like the world's ugliest picture, and we're not really sure what it's trying to tell us. But if you have a listing of possible roots, then you can kind of whittle through your list and your picture without finding them. All right, fundamental theorem of algebra. Okay, it's the moment, guys. The fundamental theorem of algebra has a lot of components, but one of the major components is to understand exactly how many zeros one should be finding. You guys already know this though. Whatever the degree is, that's how many zeros you should be finding. But we have run across moments where like a cubic only has 1 0 that shows up 3 times. Okay. We've seen examples of a quartic that had 2 different zeros, but they both showed up twice. So that's why it was adding up to 4. But the idea is, whatever the degree is, you should be able to find that many solutions. So there's one more component to this, and it's a big one, so you guys need to highlight this in your notes. The conjugate root theorem states that complex solutions or complex roots come in complex conjugate pairs. So for instance, if you do some work or you are told that 2 plus 3i is a solution, that means 2 minus 3i also has to be part of that solution. They have to come in complex conjugate pairs. That also works for irrational roots. So like 2 plus square root of 6 would have to be paired up with 2 minus square root of 6. So what'll often happen on your test is I'll give you some clues. I'll say like, oh, there's a solution at 3. And there's also a solution at 4i. Well, guys, if you know there's a solution at 4i, what else do you know? There's a solution at -4i. Very good. So it's a bit of a trick question because you got to know the conjugate root theorem. Okay. All right. Are we on the back yet? No. All right. So example in your notes here, or not. Where's this example? Oh, right there. It says, write a polynomial function of least degree with real coefficients in standard form that has a 0 at 0, so there's one of them, and then has square root of 2i as a 0. Now, I don't really like the way that looks. Usually we write it as I squareds of 2, but you know what they're trying to say. All right, guys, let's think about this. You have a polynomial. Call it whatever you want. I'm going to call it p of x. What would a factor look like if it has 0 as a solution? Yeah, you can say x minus 0. Some of you are just saying it says x. That's the same thing. I'm with you. Okay. And then if one of those zeros is I square roots of 2, his factor would look like this. X minus I square roots of 2. But is that it? No, because his conjugate pair also has to show up. So his conjugate pair would be x minus a negative I square roots of 2. Guys, do we say minus a negative? We say plus. So you have to know that the pair shows up. But we're not done. Because it says real coefficients. That means you cannot stop until your answer only has real numbers, no i's. So this one's fine. I'm not worried about that one. But let's consider this. Let's see what happens when you multiply two conjugates together. X times x is x squared. What's going to happen with the outside and the inside terms, though? That's kind of beautiful. They're going to knock each other out. Okay. And then negative I squared roots of 2 times positive I squared roots of 2 is going to be a negative I squared times 2. That's weird. What's I squared again, guys? It's a negative 1. So this is like negative times negative 1 times 2. What is this last term, y'all? It's a positive 2. So that green box is actually just the factor x squared plus 2. Those are all real numbers. That's excellent. And then you can either write x minus 0 or just write x down here. So this is going to be the challenge for us tomorrow, is setting it up won't be too bad, but getting it to the form that your teacher wants is going to be kind of awful. What a jerk. Haha, that's me. All right, so for today, as far as homework goes, you guys have enough information now. You can finish 2.3's bookwork. You can try, I would start 2.4. So like for instance, let me find it. Ugh. The first few questions of 2.4, you'll be fine with. I would probably not look at 35 or 37 yet. You'll get nightmares if you look at 35 and 37. But for like 2.4's bookwork, you want to get a head start on page 127? You can for sure do numbers 2 and 3. Number 9's a story problem, so I know how you feel about those, but try them anyways. You could probably stop there. Leave the rest for tomorrow's fun. Okay? So just so we're clear, you're finishing 2.3 and you're starting 2.4. Got it?